Hello, everyone, and welcome to Gecko's latest webinar, Technology to Reduce Forced Outages. Our hosts today are Dave Hunt and Will Barley. They will discuss how robotics, software, and advanced analytics provide the data and insights needed to increase boiler uptime and drive efficiencies across the entire maintenance value chain. Dave is the Director of Power at Gecko Robotics. He received a bachelor's in science and chemical engineering from West Virginia University. He was hired by Siemens Environmental Systems and Services as a startup and commissioning field engineer. Over the past 14 years, Dave has spent his efforts dedicated to finding, identifying, and solving for metal wastage of mission-critical assets in the power industry. Dave has been with Gecko since 2018 and strives for the safe operation of all equipment. Will joined Gecko in 2021 as a director of forward deployed engineering. He joined Palantir in its early years, where he embedded with government clients to create new solutions to their most vexing problems. For almost 20 years, Will has spent his time creating data systems and tools that accelerate operators and improve business. Will graduated from Yale University with a bachelor's in computer science. Before we begin the webinar, I would like to cover a couple of housekeeping notes. All attendees, microphones and videos are disabled. If you have any questions for the presenters, please submit them at any time during the presentation through the Q&A function at the bottom of your Zoom screen. If we do not answer your question during the webinar, we will follow up with you at a later date. Lastly, this webinar is being recorded. All registrants will receive a copy of the recording within a couple of days. With that, I'm going to hand it over to Dave and Will. Gentlemen.
Thank you, Allie. Hey, it's a pleasure to be here. Thank you for everybody for attending either live or if you're watching this on a recording. It's great to have you. So Will join us here in a moment. So I'm going to lead us through a couple of things. But first thing we do is always talk about safety. So here at Gecko Robotics, it's a new year, just like everywhere else. So we want to make sure we check our safety equipment. That applies to our seatbelts in our cars, harnesses, maybe ladders, safety glasses, hard hats. Hard hats do expire, believe it or not. And you know, my thing that I always do every year on New Year's is replace the batteries in my smoke detectors. Something that needs to be done routinely. And it's actually funny. I got a text message from a friend that said, "Happy New Year! Don't forget your batteries in your smoke detectors." So make sure you take care of that both at work and at home. So let's start with some foundation and fundamentals and theories and principles, and then we'll evolve into really what's going on in the environment and the world that Gecko sees. So let's start with ultrasonic thickness testing. You can see that there are known velocities of sound through steel or any solid or medium. We have it both here in SI and in metric units. And so ultrasonics measure the time for an echo to be heard through a medium. That gives us a distance or thickness based on knowing the time and the velocity. And so the resulting echo or series of echoes is called an A scan. And so that is computed. You can kind of see that in the imagery here. So that then gets converted. We measure the distance between the peaks, and then we can usually determine a 3-digit number, and we pile it into a spreadsheet. Whether it's an SI or metric, doesn't matter. It usually results in a portion of an inch or several millimeters. And so anyways, at that point, we now have something that's visual and quantifiable that we can easily look at, judge, try to make sense of. And so over the last 8 years or so, Gecko has been collecting billions of data points. You kind of see one of the robots here behind me that's been doing that, but it's done it in the power industry, oil and gas, defense with some of the destroyers and aircraft carriers. And so we found two things out during our existence. One, that using robotics to collect data is helping customers reduce failures. However, we're not driving failures down to zero. So failures are still occurring even with the use of robotics to collect data. So Gecko said, let's step back. Let's look at the codes and what is kind of governing our built world. So we looked at the Navy first. And so they've recently updated their code from 1995 to 2014 to allow digital radiography as opposed to conventional. So we're glad that they're up to that, but that's still been 10 years. The National Board, which governs boilers here in the States, doesn't really define a number of thickness or data points required to make remaining life calculations. So we could have 1, we could have 100, or we could have 1,000,000, but it's up to us as engineers to determine that. If you have above ground storage tanks, API 653 actually does give us a value, which is good. However, it's only 5. And these codes were largely written because at the time, manual collection of data was necessary. We didn't have robotics or advanced ways to deploy data collection. And so the codes were written and are a bit outdated. So that leads us to the tools that we have to digest these: spreadsheets, software, visualization. And what they've done is you either have 1 data point, maybe 5 data points like the API 653, maybe you have hundreds or thousands or millions that you've then now compressed into a single number. Like we saw earlier, we have 600 A scans. We need to generate 1 number that we can try to rationalize. That A scan gets lost in that compression. The other 599 do too. Or the histogram, like the distribution, if we want to see the bell curve of those readings. And so that really makes our built world tough to accurately maintain with decisions. And we can lose productivity. We can also miss what I think EPRI calls the golden tube, but that's the tube that pops, or the asset piece that fails, that ultimately takes us out of service or creates a forced outage. And so those tools, because they're a little outdated, they don't give us the ability to double click. And so as Gecko has been looking at this, we've understood that double clicking is really paramount in understanding the data or the number that we're using to make a judgment or a maintenance decision. But unfortunately, right now, we don't know if that number is the absolute minimum of a data set. Is it the average of, say, the bottom 5%, maybe 10%? Is it the mean, the mode? I hope it's not the max, because that probably doesn't create too much advantage for us. But we don't really know, because we lose that fidelity of the data sets because we've compressed it down to make it usable. And so while that helps us, kind of observe, it doesn't allow us to obsess. So if we double click, we can obsess. If we zoom out, we can observe. So knowing all of that, Gecko then started to look at some of the regulated utilities here in the United States. And as part of some of the organizations within the government, they are asked to quantify their O&M costs per megawatt generated, per customer. They back out some fuel costs and things like that. But if you look at the middle graph here, some of the customers can generate a megawatt hour for about $20 in O&M costs per year. Other companies at the bottom, unfortunately, they're about 3 times less efficient. So it costs them about $70. And so we started looking at that, like, why can we have such a disparity for the end user, the person turning on their light switch, but also the people that are running the plant? Why is there such a big delta there? And so we've really determined that some of their O&M cost inefficiencies, unfortunately, it's not what they're buying. They're still buying the same thing: tubes, maintenance strategies, different things, but it's sometimes how they buy it. They have to overnight a tube on a Saturday that's also a holiday weekend. That's going to have an intrinsically higher cost than if we bought the tube 2 weeks in advance. So we then started to plot what we're learning. So over the last, say, 20, 25 years or so, tube leaks and forced outages are trending up. It's just reality. The aging infrastructure in the States hasn't allowed for us to build new coal plants or very few new fossils. So we are now running these things longer, maybe past retirement dates, extending retirement dates, but kind of creates 2 different options or scenarios that can play out. The first one is that aging equipment combined with an aging workforce. Maybe your SMEs are retiring. New folks maybe don't want to get into an industry like that if there's a potential short career, if you will, in their kind of purview, and that can create misguided or like unintentional maintenance that isn't going to solve our problem. We did things, we tried our best, and it's not our fault because we only had so much data or only certain tools to create those scenarios. But Gecko actually believes that there's a different approach and a different outcome that can actually show up here, and that's option B. So option B, as you can see, we're taking those tube leaks and forced outages downward, and we're trying to get them as close to zero as possible, because if it runs reliable, we don't have to get called in on the 4th of July weekend or miss Thanksgiving with the family. So as we started to plot this and look at it, before robotics, we had a certain level of tube leaks in the industry. As our customers started to integrate robotics, they were able to decrease some of those asset failures and increase reliability, but it didn't get it to zero. So what we learned is that inspections, regardless if it was manual, robotic, or any other way, are just a snapshot in time. So it's one data point instantaneously at that time, and that corrosion and erosion rates are not linear. So we can look at two different data points, and we'll have to assume it's linear, but Gecko's learning it's not linear. And that wear pattern, or those wear patterns in an asset, are not uniform. They're different. Could be different on the north side or the north wall versus the south wall or the south side. Maybe the wind is influencing it. There's a lot of different things that impact this. So taking a handful of data points and kind of generalizing it for a whole tank doesn't necessarily get us all the way to zero, or a handful of readings on boiler tubes doesn't get us all the way to zero. So data collection is great, but it has to be paired with analytics that can handle that many data points to really drive the horsepower necessary. So as we look at a customer that Gecko has partnered with, between 2019 and 2023, they tried different approaches. They collected manual UT data, they collected rapid ultrasonic gridding with the tokas like this, and they saw a small difference in tube leaks. So they did decrease, they went in the right direction. However, again, we didn't get to zero. And so Gecko had to help find them, what happened? How are we getting the results all the way to zero? How do we really achieve that? And so what Gecko started to look at is, okay, let's start at the ground and let's get as much data out of people's heads, out of filing cabinets, out of desktops, hard drives, whatever it may be. Let's find that failure history. Let's find that repair history, any operating data we can get from Pi or from Canary or any of those other systems. So we'll start there. We'll then add the other data layer, which is the rapid ultrasonic gridding, UT, maybe drone visual imagery, anything else that was collected on the asset. So let's pair that now as well. And if you take those two data layers, mesh them together into a platform, you start with the validation and the aggregation of the data. And then we're going to build digital twins. And once we have that, so we have an interactive model, we need to start doing predictive models. We can use the power of AI and some of the other tools out there to really supercharge this data that's currently in a digital format, to really create outcomes that are actionable, that will change our future. And so Gecko has built some apps where we can look at a fleet across a large customer base, all the way down to the site, and then we can get very, very granular down to the asset, and create repair plans and actionable strategies immediately. That also pairs with some of the other customer apps that you already all are using. Right? We don't want to take those away from you. We know they add a lot of value to your business. So these get paired with them to enable you all to make better decisions and run more reliably. And so the process is pretty simple. After we've aggregated all that data, we start collecting more data, right? In the outage, whatever window you have. And then we leverage what we're calling cantilever. And Will's going to demo it here in just a moment. But the goal again is reliability up, force outages down, as close to zero as physically possible, and then use cantilever and the abilities and the tools within the software to create those actionable plans right away, and then look forward in the future at what should we do by next time? How can we order some of our materials for next time? And then after we make it all the way around to that next outage, let's collect more data. And so I'm going to turn it over to Will, who's going to really demo the strategy. But let me turn to Ali. Ali, are there any questions from the audience that I can answer?
Yes, Steve, there is one question. Someone is asking, is this a one and done type approach?
It's a great question. So the way that Gecko thinks about it is one and done. It would be great. However, every year we go to the doctor and we get a physical, and they run a battery of tests on us, and they want to ensure that all parts of the human body are functioning properly, and that we can make strategies, maintenance strategies with a human, as you know, according to what we're seeing. So the same thing here with Gecko. We need to continually collect data to feed the software so that it can continue to create the right recommendations and procedures on how to continue to operate reliably. All right, Will, over to you.
Okay. So this is a recent boiler that we scanned. And just to give you some orientation here, so all of the colored information that you see here, this is boiler tubes. This is the data that we collected, ultrasonic thickness readings on boiler tubes. So all of this is boiler tubes. In fact, if we look all around, there's 4 walls to this boiler, 4 main walls. There's a roof here. There are wing walls off to the side so that you can see them. This whole structure is piping. All of this is pipes. And this is about 70 feet vertically of pipes. And to give you the best view, I'll actually flatten it out into 2D. So we've got about 70 vertical feet. We've got a side wall, front wall, side wall, rear wall of the boiler. We've got the roof up here. We've got 3 evaporative wing walls placed kind of side to side right here. They slot into these 3 slots over here. We've got 2 superheat wing walls that slot into these 2 bottom slots. So we've got a lot of tubing here, but just to give you the lay of the land. And so we've also got a lot of colors going on here.
So Will, this is great, man. Wow. Great digital twin. When you guys were on site, you collected all kinds of data. Like, can you tell me more? Like, can we see past failures?
Sure. So we can flip on past failures, and you can see a few down here, up here, right down here. Well, let me zoom in on these. So if we look at how the boiler is thinning, you can see where some of the past failures have been. So look at these blue dots. These are 4 failures right in this area. And we've got information about each of these failures. Some of it we've redacted to protect our customers' privacy. But these are all, pieces of information that we pulled out of the customer's records. They had some paper records. They had some information in their heads. But we pulled this all together so that you could see both the current condition with the history in one place.
Wow, that's great.
Will, we do have a question from the audience. Somebody is curious of what the colors mean when we look at this 2D model.
Sure. Yeah, so the colors are right now describing thick and thin. So we're looking at thickness. These are the readings that we took. How thick are all the tubes? And red means thinner, green means thicker. You see some big jumps here. So this green section down here, I'm seeing readings around 315 mils. And just above it in the orange section, I'm seeing readings around just under 200 mils. So we actually have a change in nominal, that there's different thicknesses of tubes in play here. But that's what we're seeing. Red is thinner, green is thicker.
And another question from the audience, Will, is how is the data aggregated to create this model?
Sure, yeah. So this is about 30 million readings. Like Dave described, putting that ultrasonic transducer, that ultrasound machine on the wall creates a reading. Well, we did that about 30 million times in this case with the help of our robots. And we've distilled it down into a bunch of grid cells. We call these bins, but it's little squares And what we're seeing here is we've got about 100,000 of these squares. So we've shrunk the data down to that size. But underneath each one of these squares is actually a lot of readings. So each vertical line here is a single tube. This is a single pipe. We got a pipe next to it and a pipe next to that and a pipe next to that. And the squares demarcate a 3-inch section of a tube. So we got 3 inches here, 3 inches, 3 inches. And we can actually look inside. What do we see inside these? We can kind of unwrap these little cells and see that there's about 100 readings in this cell. So in 3 inches, we're collecting 100 readings right here. In fact, we can break that down to left, center, and right side of that tube.
Excellent. And can we see more about the data? Is it just
Sure.
left, center, right with some dots? What do we got?
Yeah. So in this case, I think that the first thing that jumps out to me is we've got a distinct wear pattern on the right side. We've got all red dots on the right. We could look at sort of a histogram of the data. What's the breakdown of all of these readings by thickness? So this blue curve here is the recent inspection that we did. And it's showing, hey, you've got a lot of readings that are in a reasonable range, and you've got a fair number of them are that are getting pretty thin. It's that right side that we saw. We're also seeing another histogram from a previous inspection. So here on this 3-inch section of tube, we've got, maybe 50 readings from 2020.
Excellent. And so it looks like the tube has changed in thickness. It's increased over the last 4 years.
Yes. Yeah. So in 2020, it was thinner than it is today. So this tube got down to, around 80 mils in 2020. They found it, fixed it. So they put more metal under this tube. You can see it's substantially thicker. While at the same time, its right side is thinning out really quickly.
Mm-hmm. So that gives us a window into maybe the process or how that tube is responding in the environment that it's in. That it's not necessarily the whole tube is wearing away at an even rate, but now by double clicking and getting very granular, we can actually see if it's left, center, or right within a 3-inch bin.
That's right.
Wow.
Okay, so that's taking us really deep into the 100 readings that are inside this 3-inch area. When we wrap that all into bins like this, we're left with about 100,000 of these 3-inch areas covering the whole boiler. So one of the things that was really interesting to me during this outage. So we got this data 2 days into the outage. This is all happening during a planned outage. This is during a short 5-day outage. But on day 2, we've got all of this data.
Mm-hmm.
So the plant wants to know, well, what did you find? What do we have to do? We've got 3 days left. What are we doing?
Sure. Makes sense.
And so what they asked us to look for is what's under 150 mils. And we asked them, well, how did you choose 150? And they said, well, we started at 100, but we had leaks. So we chose 110 as our flag level, but we still had leaks. So we went to 120, 130, 40, and today we're at 150. And so we said, well, here's what's under 150. This is what we found for them.
Wow, that's looks like quite a lot.
Yeah, this was a lot. They were not happy with this answer. When they looked at this and they're looking at, we've got 3 days left to close up this boiler. They can't resolve all of this.
Yeah, it seems like something that's insurmountable right away. Is there a way to toggle to see what we did last year, or check some data from 22?
Yeah, I mean,
give us more
it's a
window?
good question. Like, it's a big surprise. What did they see in 2022? So here's their 2022 inspection. So they ran this UT inspection through a third party, and they gathered it manually. They sent a team of guys around the boiler everywhere with ultrasonic thickness meters and took a lot of readings. They took thousands of readings. They did a very comprehensive job. And here's that whole scan. So you can see we're looking at the same boiler. You see the big cutouts up top. You see the cutouts for those wing walls. They got a lot of data.
Yeah, it also looks like there might be some gaps between 20 and 30 feet. Like, is there more that we can tell from that?
Sure, yeah. There's a big gap here. Not able to collect data everywhere. Let's look at what that looked like in 2023. Right in here, between these two wing walls. So yeah, they weren't able to get information here last year, but this is a pretty important area. You can see there's a lot of red in this area. This is a pretty high wear area. So it is hard when you're doing this manually. It's very hard to be comprehensive. Their question was, what's under 150? So when they look at that manually, they found answers. Right up here, there's a bunch of red by their air boxes. They fixed this. They didn't get any signal down in this important wear area. And when you flip to 2023 and ask the same question, one of the big differences is just, this is what happens when you look everywhere. You find the problems everywhere. And so this just turned out to be too much.
Yeah, I think somebody said it's going to fail where you don't inspect. So the good news is you found it, but let me ask, I mean, 150 is the threshold, but do all of these areas need to be repaired?
Well, all of these tubes are below 150 mils, but some of them are going to be fine for years. They're wearing away at different rates. There's high wear areas, low wear areas. Some of these tubes are going to fail before next year. Some of them are going to fail before their next outage. These are going to become the tube leaks that interrupt operation. So that's the real key, is like, how do we look at this by time instead of by thickness?
So you're telling me that there might be a 160 or 170 that actually could take them out?
If it's in a high wear area, it could be.
So if we double click and obsess with the data and look at it on a micro scale and then zoom out and observe it, you're telling me that there's potentially a different way to digest this data and make repair plans?
Well, I think the opportunity is to get more specific, more clear. Which of these tubes are really the threats? Which of them are going to fail in the next year? And which do we have more time to solve? So part of what we do here is we actually take into account the differing rates of wear so that we can actually look at how much life is left in every tube. So this is that answer across the whole boiler. And if you want to operate the boiler for 30 years, here's the areas that may be concerning, or if it's 15 years, there's that. But what we really needed to know, so we were on the clock at this point. We had 3 days left in this outage. We needed to know what was going to fail before the next outage. That was the first threat that we needed to solve. And here's the answer. This is all the tubes that have got less than 1 year of life left.
Well,
What'd you do? Well, Allie, is there a question from the audience?
there is. Somebody is curious to know why those areas were wearing more than others.
Sure. So this is actually something we discussed with the plant. And what they said is, I mean, take this area, for example. This is the area that they didn't get any data on last year. But look at this. There's a bunch of red in this area. What the plant explained is they've been adjusting their airflow, and that changes both the location of wear and the amount of wear. And this right here is turning out to be a very high airflow area. So we've got a wing sticking out here, and there's a bunch of air being sucked up through between them. And it's creating a lot of erosion in this spot.
So while you were on site, weeks prior to the outage, you learned about past changes to, say, nozzles or airflow in the boiler that can change localized velocities of the bed ash or whatever the process is. And that can then change how we've potentially looked at it in the past, because now we have new operating conditions.
Yeah, in fact, in this boiler, the highest wear areas used to be on this rear wall over here where you don't see any issues. All of that has moved. So these things don't just stay static.
Hmm.
All right, Dave, I think you asked, well, so what do you do? So we've identified the areas. How do we actually operationalize this? Part of our goal was, if we give you a mountain of data, that doesn't necessarily make it easy to hand something to your welders. So how do we narrow that gap to nothing? So here's how we translate this into a plan that we can hand off to welders, and an hour later, work is actually happening. So first of all, we've done a little bit of work to get to this point. We've identified what matters to us. What is our target for the repairs in this outage? And we can save this analysis. I'll call it 1 year of life. And so this analysis and how did we get here actually gets saved in the system so that when we come back to this, we're not having to try to remember how did we reach those conclusions. Okay, so these are all of our saved analyses on this boiler. There's a bunch of ways we've looked at this. And let's see, 1 year of life. Let's turn this on. Okay. All righty. So let's save that one more time. Okay, 1 year of life, save. Great. Okay, so while we wait for the system to crunch that, what we're going to do is we're going to create a repair plan. So we'll call this must fix because that's our first priority. We're trying to figure out what are the tubes that we absolutely must fix. Okay. And at the same time, we've got to acknowledge that the plant coming into this outage has plans. They've been working for the past year to figure out where they're going to install new panels. Those are represented here. So the plant already had plans to install new panels here, but we're gathering a bunch of new information. This is a chance to actually change the plan at the last minute if it's very beneficial. So we're keeping that in mind as we go. Okay. My saved analysis is sort of highlighting the areas that we are targeting. And now that we have a new plan, we're actually going to, let's see, not that. Okay, create a new plan. Must fix 1 year. Okay. Okay. So what we're going to do is we're going to have the system automatically crunch all of this and tell us, what is the best location for the different types of repairs. And we're going to give it a number of inputs that represent how do we want it to incorporate our SOPs around repairs. There's a bunch more details that come into when you're actually going to weld things. And so we've given it that answer, and the system has given the optimal placement of where should you actually do welds, panels, etc. So you can see highlighted in gold, these are our problem areas, and the pink boxes are boxes that we are going to weld over. Okay, so this gives the answer to what do we have to do and what should we go hand to welders right now. We'd export this to Excel and get them started this hour. It's about 61 square feet of area.
Wow, that took like 30 seconds for the system to triage 30 million data points into something usable. So when you showed this to the customer and you sat down with them and you got a couple of days to go make these, what was the reaction? How did what unfolded next?
Well, when they saw that their problem was no longer insurmountable, and instead, this is a plan that they were sure that they could execute. This could easily fit within their outage window. They're very happy about that. They sort of like had this certainty, like, hey, we're dealing with the tubes that are absolutely going to leak. In fact, they told us, if we need to take an extra day to solve all of these, we'll do it because we know which ones are going to fail on us. So they ended up with extra time, actually.
Nothing like having extra time during an outage. I don't think anybody said that. So then what? What do you do with the extra day?
Well, that's what they asked us. Hey, we're we're basically spending a bunch of money to have welders here right now. How do we get the most out of them? And so we looked at, well, okay, what's going to fail just behind these tubes? It's not going to fail before the next outage, but what's just behind that? What's next up? And what we planned out was we gave them a plan that said, hey, here's all of the nice to have tubes. These are tubes that are going to come up. They're going to need repair in the next 2 to 3 years. But they're not going to fail this year. So it's okay if you don't fix them all. But we gave them a lot of additional scope. It looked like this.
Wow. And so you can just layer those things on and off based on time and resources and availability.
Yeah, we gave them about 300 total square feet, but we showed them the particular 50 square feet that had to be done, of course.
Yeah. Were they able to see efficiency gains either by welders or others that were, moving around and supporting the outage?
Sure. So we gave them enough more work than they could do. Here's how much they ended up being able to execute. So it's about a third of the nice to haves, but it's about equal to the must do's. So one of the efficiencies they gained was, if you have a welder sitting right here doing what must be done, but just adjacent to that, there's some tubes that are going to fail in year 2 and 3. Having that guy just grab those up at the same time versus take all of his equipment, go down a few flights of stairs. They got a lot of extra welding out of that.
So you're really optimizing the time of that welder, that skilled labor, to try to get as much production in that time window you have for your outage. That's a added kickback of this planning. Is that what?
Yes, it's all time.
Wow. And I see a repair cost calculator down there in the corner. Is that like, can they modify that based on their own inputs?
Sure, yeah. You could easily change, your estimates of how much does overlay cost you per square foot or panels. And we're using this mainly when we're sitting with the plant, figuring out what's the plan that we're going to go execute. And it's got to fit into all kinds of budgets: time budget, money budget, materials. How many panels do we have sitting around? And we just did a lot of automation here where the computer is crunching all the things that we asked it to do. But we also need to incorporate the knowledge of the most experienced guy in the room. He might know we should really shift that panel around.
Mm-hmm.
And so when we do that, the numbers change. Our square footage changes, our time changes, our money changes. And so this is a way to help, in a live way, get to the right plan very quickly.
Excellent. And so as you do these plans, if you were to toggle on the known repair plan of like the panels that they had started with, then
Sure.
that can be incorporated into that cost repair. And okay, yeah, it looks like
Yeah. So we
couple
added
button clicks.
48 square feet of panels, those 4 panels that were planned.
Yeah.
Yep. That adds the cost. And
yeah, and it looks like there's some overlap even where areas we found that were going to need to be replaced anyway. So I think that can help them understand, how to better use those panels and those welders and that skilled labor to really solve for reliability issues.
yes, I've been with customers where they open up, they're in an outage, they don't know exactly what they're going to find, and then maybe they collect a whole bunch of data, and they've got 2 panels sitting out in the shed, and it's a little bit complicated to get to the answer of like, what's the best place to put these. So we wanted to just squish that friction to 0 to help them.
Wow.
Well, we do have another question from the audience. Somebody is curious to know, how do you integrate the areas/points that are not scanned into the model?
Sure. So like areas that you really haven't looked at. Maybe, so you just saw all of the data that we've got here, but there's other pieces to this boiler. Yeah, those are important too. Those can be failure locations. So those can be very important to scan. You got to do those manually, traditionally. You still have to do those.
Yeah, absolutely. And I think, targeting where your failures are currently occurring, I think they were able to solve for the largest pie slice of what was taking them into forced outages. And if you can start there, you can make the biggest impact. And now that they have a better handle on that, I think they can start chasing some of those, if you will, nice to haves, right? The areas we haven't looked at traditionally or put enough attention on because we have something bigger in the room taking us out or causing us headaches and agony.
And Will, another question, should you need to take manual readings in any area of the boiler, are those data points able to be integrated into this model?
Sure. Yes. In fact, when we looked at that 2020 plan, this is a pretty extensive manual scan. So this is one of the larger manual scans that you can do. But yes, we've got all of this in the system. So you can see red, yellow, green here. All these readings were manually collected, and we've just integrated it right in the system. And you can plan your repairs based off of this.
And someone also asked, how often do you need to complete these scans?
I mean, this is a tool to help power plants and operators of other assets. So it's really up to what they need. What we found, I could say what happened here. So I mentioned how the wear pattern changed. When this plant looked at this data, they said, oh my gosh, this is kind of confirming what we've suspected. The wear pattern has shifted, and we've been making operational changes. The amount of wear has increased. And so it was really helpful for them to see with a lot of data some of their suspicions. And their reaction was, we want to do this again as soon as possible because we're continuing to need to operate this plant. Things are continuing to shift. We're continuing to dial knobs. That was what this plant said.
Excellent. Yeah, operational data matters. If you ran close to 8,600 hours in a year, that's going to dramatically be different, wear patterns, wear rates, than if you ran 4,000 hours in a year. So absolutely, I can see how continued data input, I think to an earlier question is kind of mandatory, regardless of how that data gets collected, really continuing to feed the system so that the algorithms and the AI can just be stronger and make even, better recommendations as it continues to
Yeah, one of the things they were saying was, if you take one good scan of their boiler, you get a great sense of all the history built into this metal. Where have things worn away? Where have they not? But you're kind of looking at a big slice of time. And so one of the reasons they wanted to look again as soon as possible is they wanted to get really dialed in on what's happening this year, what's happened since last year. That was another reason that they wanted to look more.
And another question from the audience asks, does the AI model have the capability to make recommendations on flow rates or other operational variables?
That's a good question. So I can just speak to a couple examples I've seen. When you get a really comprehensive picture of condition, you see some of the effects of those settings. You see the effects of flow rates, for example. And so things that we have discovered are not in this boiler, in other boilers we've seen flame impingement. So you have burners that are mistuned that nobody was really aware of until they got a good picture of the effects that were happening. So sometimes this is a powerful way to see that you need to make some operational adjustments.
Yeah. So you can potentially tune burners, change airflows. I think it requires a feeding of operational data into the system as well, so that you have that knowledge base, if you will, to make that. But yeah,
and then this provides you very detailed feedback on what are the effects of those changes.
And you can then begin to look at independent variables that potentially created that new outcome.
Mhm.
Yeah. Wow. Excellent. So thank you, Will. I mean, that was great. That's exciting to see. And I think you were able to pull up like and create repair plans in 15 to 30 seconds. Like that's quick, especially if hours or days matter. Now you're doing it in seconds. So
Yeah, it's fast. There's a lot of scrutiny required, and so having some automation to help the people trying to do this,
yeah,
it's great.
awesome. So, I mean, we're trying to change the future, and so are they. And so, if we look at, option one or option A versus option B from the slides earlier, the current trend is that red line before, partnering with Gecko and helping to try to bend that curve, and so that they can try to judge where they're going to be in 2038. And really, that's a proposed program. We're still, again, trying to bend that further and keep that about as flat as possible. But continued monitoring of operation and data, that's all going to help make that model even more powerful as they continue. So like the roadmap really on how this came about, like Will, like I said, you were on site for like 2 weeks or prior to the outage. Your FDE team was talking to their subject matter experts. What problems do you have? Where were the repairs? Maybe that information was in their head. Maybe it was in a filing cabinet. Right?
Totally.
There's 25 years of knowledge at some of these people.
Reality.
Yeah.
Yeah.
And so you have to extract that because it's all usable data. Let's put it somewhere and warehouse it where we can make it actionable because we need history, right? It's the double clicking of whatever happened before. And then where have the repairs been? I think we looked at failure analysis that you guys were able to collect.
Yeah, if you know that you replaced this panel or this section in 2015, that's much different than we have no knowledge of that or no records of that. The wear rate might be estimated to be twice as high if you really did repair it. So the real wear rate is dramatically higher if you can bring in the knowledge that you have, whether that's in your head or in filing cabinet.
Yeah,
that's okay.
Yeah. And so all that leads up to, okay, it's game time. Let's get this thing in there. Let's go collect some data points. You were on site for all of that. That takes about 12, 24, 36 hours, depending on, size of it, how many robots go into it.
Sure.
Solve for all that. And that's really then like the crux of it. Now you got to put those analytics. We've got all the data. We just saw 30 million data points, created into a system that can handle that many, can look at past, can give us histograms and all that kind of stuff. And that's really what gave you guys the ability to make those repair plans and those maintenance strategies in real time to say, okay, we have 3 days. What must we fix?
Yeah.
What would it be nice to fix? And then how do we then store those records? Because we don't want to leave them in somebody's head. We want to allow anybody coming through, corporate, other support.
Make it easier the next time.
Absolutely.
Yeah. Next year's plans will be highly affected by this year's work.
Absolutely. Yeah. And so some of the things that, Will demoed there, showing how the scatter plots, the imagery of the actual tube, we can, you highlighted there was a lot of wear on the right side of one of those tubes, right? Maybe we're more efficient and we can send the welders just to focus on the right side. That can speed up our process or create more productivity in a shift. You can also look at those histograms. We saw the one tube had increased over time. In this example, it looks like it's decreased, and we can kind of see, each tube or each bin, 3 inches of tube is actually unique and needs to have the ability to double click so we can make the right strategy for what we're seeing instantaneously. And so, you also showed this, like, the 150 strategy was really what they were tackling. It kind of created too much. It was overwhelming and it didn't really solve the problem. That's how they were doing it in the past, but they were still having failures.
Leaks,
And so as you looked at remaining life of the tube and then started to develop those strategies, you were able to then look at what will fail in 1 year. So that's the must-have, the blue box that's here. And what is a nice to have? We have extra time. We have extra money. We want to make our welders more efficient.
We could give them clarity. I mean, that if I were sitting in that seat, all I would want is clarity. You know, what do we have to fix? What can I not close up this boiler before fixing? Just having a fuzzy idea that leads to, well, we did the best we could and we closed it back up, and there's those failures lurking in there waiting to happen.
Yeah, those golden tubes that Embry talks about that take us out. But you didn't stop there. So the digital turned into the real.
Sure. Yeah, that's just about compressing that friction that everybody faces. Like, hey, we've got hours left to go. We just got a bunch of data. How much work is it going to take from here to someone's actually welding the right thing? And so we wanted to compress that to zero. So we figured out what's the plan, and then we have to translate the plan back into reality. We have to put it on the walls so that it's imminently clear where every weld has to happen. So we did that.
And you guys even, I think I saw analysis of paint colors even to try to make it even easier. Because as you can
Gotta
see,
get the paint colors right.
you know,
In those lighting environments, you know, you don't want to get any confusion happening with your welders.
you know, and if it's carbon, it may have flash rusted. If it's overlay or some stainless material, maybe it's a gunmetal color. So what's the easiest for everybody that's attacking the problem in the real world to see and understand, and where are our must-haves, what are our nice-to-haves, so that we can really dial that in and achieve all of these things. And so I thought that was really unique that you guys even went all the way into paint colors of what creates the best visualization for the people doing the work.
Yeah, it's not a fancy feature. It's like we learned red is a color that gets very confused in this environment. And so if you have any confusion, it means someone is definitely going to make the wrong welds, and you may not get your tube fixed. That is going to fail on you. So you have to get these things right. You have to go to the last mile if you want to stop tube leaks.
Yeah.
But we wanted to make that easy. So that's what we've been working on.
Excellent. Yeah. So again, we looked at asset health here, and we made instantaneous repair plans. We're looking at future risk assessment with them, right? We don't stop there. We want to continue to see what's it going to look like.
Yeah, that was a picture of what does this all look like in the midst of a 5-day outage.
Yeah.
All done, start to finish in a 5-day outage.
Right.
We also do this more strategically.
Yeah.
Looking at how can we economize, 5 years of repairs efficiently.
Yeah. And so, just as they had planned a couple of panels there going into this outage, we're helping them try to plan where they may need panels in future outages so they can have that raw material and feedstock on site.
Get very efficient repairs that way.
And we know there's going to be some discovery work, but we can boil that down into very manageable pieces, and we can plan for the bigger pieces where we may not be able to weld on it anymore because it's just reached its end of life. We need a replacement.
Yep.
Yeah. And we can stack rank that prioritization, I think. And I think that you showed that with the cost tool as well, that, hey, a panel has intrinsic value. Weld overlay or thermal sprays or different strategies have another intrinsic value. How do we optimize for dollars and time and not just what's easiest, if you will? Because easiest doesn't always solve our problem.
That's right.
Yeah. And this is something that can be deployed across 20 boilers in a fleet, 100 tanks, 20 customer sites. We've seen that already being developed and integrated and adopted.
We didn't talk about it today.
Right.
The fleet picture of this brings in other questions that are important to optimize. Where are you spending your money and your attention?
Yeah. And I think that goes back to one of those charts we showed earlier about O&M dollars spent per megawatt hour generated, like at these regulated utilities. They operate 30 sites, 50 boilers, something like that. So now they're looking at it as a bigger picture of how do we minimize O&M dollars, optimize reliability and uptime, and really create something that's beneficial for our customer who's trying to turn on the light switch.
Yeah. These are hard problems. I love when we can make it just more clear, make the dots connect, make it easier to reach those kind of outcomes.
Yeah, absolutely. Well, I think we've come to the end of it for right now, but I'd love to turn it back over to Allie. Are there questions that's come in from the audience?
Yes, Dave, there are. So one question somebody's asking me is what kind of boilers are a good fit for this versus those that may not be? For example, coal-fired versus natural gas versus fins, which is versus large and small diameter tubes.
Yeah, so tube diameter, we've seen a gauntlet of it. I think down to an inch, so that's about 2.5 centimeters or so, upwards of I think some 4-inch tubes, maybe some 5-inch tubes out there. As behind me, there's a wall of a bunch of different sizes that the customers have graciously donated to us. So tube diameter doesn't necessarily matter too much. We are seeing a lot of CFB integration and pulverized coal integration into these systems. Natural gas, a lot of times they were converted if they were some of those older utility boilers that used to burn coal, or maybe they're looking to transition into burning coal, or sorry, from coal into a natural gas or even hydrogen or other fuel sources. So this can help in that planning of, hey, we have to spend our CapEx dollars to change out burners and gas lines and all kinds of things. But how do we also solve for, I don't want to have a tube leak till 2033 when this thing's going to go down, or 2038 when we retire this? How do we try to get all of those maintenance strategies into that CapEx in the conversion? So I think that it's not really bound by too much there. Yeah, there's a couple of things that TOCA can't collect data on, but that's data collection. There's other ways to collect data as well. And so the software is really empowered to take data that has been collected and really supercharge it and give it that horsepower needed.
Thanks, Dave. We just have a couple moments left. And as a reminder, if you do have a question, please drop it into the Q&A. And if we don't get to it today, we will certainly follow up with you within the next couple of days. Another question that we have from the audience is, can you integrate different test results such as AUT and thermography in the same model?
Will, you want to take that one, or?
Sure. Yeah. Certainly that's possible. Our goal is to provide a very intuitive, easy to understand space to bring these different pieces of information together. They're talking about the same asset. We want people to spend their time looking at something that's easy to understand, spending their brain power that way, instead of, opening different PDFs and finding different PDFs and trying to figure out how they line up.
Thanks, Will. And let's take one last question. So somebody's asking, what prep work would this require to have a report conducted? Appears you will need to have high pressure, clean boiler tubes to make sure you get accurate readings.
Yeah. It does depend on the boiler type, what their fuel is, all kinds of things. A CFB is usually naturally cleaning. Sometimes biomass can leave a little bit of debris on the wall, but TOCA is pretty well suited to get through some of that. If you're burning coal or a fuel like that, fuel oil, you do need to clean those tubes. But you'd have to do that to take manual data collection as well, whether they're sandblasting lines or maybe, doing some grinding wheels to create those areas. But either way, the asset does need to be cleaned to collect data. But the higher the fidelity and the integrity of the data, the better this platform is able to use. So as Will showed, there's a bin, 3 inches of tube, has 100 readings. That's great. That's optimal. If only 5 readings exist in that 3 inches, then we have less data to make actionable. We have bigger gaps, and it makes the system less powerful, if you will. So the more data that can be collected and fed into the machine that has a high quality, those A scans look good, they've been reviewed, they've been aggregated properly, then that really enhances the ability for this tool to work quickly.
Thank you, Dave. And with that, we will conclude today's webinar. As a reminder, this webinar was recorded, so you will receive a copy of the recording, and a special thanks to Dave and Will for our wonderful presenters. And if you do have any other questions, you can always email them directly as well, and they'd be happy to answer them. Thanks so much for joining, and have a wonderful afternoon.
Thanks so much. See you later.
See you guys.